All right, cool. So I want you guys to take out this example practice problem I was doing for the electrolytic cell, and you are looking at the copper chloride. So if you guys remember in yesterday's lesson, we looked at the achieved and the merit criteria. Be mindful that the first step in the achieved is making sure you assign things properly, and if you assign things the wrong way around, it's automatically a not achieved because that is the real basic first step. So some things to kind of remember with that assigning. When I give you a compound, I'm going to give you an ionic compound. That ionic compound is going to be in the molten form, so I melt it so that way my ions are free to move around and thus can do the electrolysis. If I don't melt it, it's not going to work. The other way this works is by dissolving it into water. The problem when we dissolve things into water, though, is that water can also be a part of the redox reaction. In order to simplify life, I've only given you molten questions for that reason. Okay? Obviously, we didn't do molten in class the other week because that would require a Bunsen burner that's really, 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 really hot, and I don't want to deal with like liquid ions because that is also going to burn and scald people badly. I don't want to do that. So that's why we did it in water, but luckily with this reaction in water, the two ions that I want are the ones that are going to be involved in the reaction anyway. So be mindful when you see copper chloride and you see this formula, don't just split it in half and then go, oh, I have Cu and I have Cl2. We want to think about the ions that are there. This is an ionic compound. So that means that when I break this ionic compound apart, this Cu is actually Cu2 plus. Copper ion. This Cl2 is just telling me we have two chloride ions. So make sure that whatever you're starting with the electrolytic cell are always ions. And then what you have are the elemental form. If you get these swapped the wrong way around, that would be not achieved. If you, for example, wrote Cl2 plus going to Cu, and then you wrote Cl2 going to Cl minus, that is also not achieved. All right? These little things do make a big difference. That's why I want to say that. I could probably give, depending on the extent of the mistake, I could probably give a conference so you can fix it, but that would limit you to an achieved because those conferences are only to go from not achieved to achieved. Okay? So do keep that in mind. So that one's that one. The other thing you need to do for the achieved is just regurgitate the definition for oxidation and reduction. And the other thing I'm going to be looking for is, do you know how many electrons are being gained or lost? Which you can easily figure out by the charges. Again, there's nothing in the assessment criteria that means I have to assess complex equations. So I've chosen very simple ones. All right? So I'm being very nice. So it should be very obvious which one's which. And also how many electrons are being gained or lost. Be mindful for things like the chloride or any of the other halogens or the halides. They have only one electron being lost for each one. So that's why we're saying one lost electron instead of two. There's two in the equation though. Are you okay with that so far? And the last thing you gotta do is identify whether or not it requires energy or releases energy. I'm going to not like this thing. I don't know. I don't know if it's just because the Wi-Fi's been buggy. All right. So that's all you need to do for an achieved. I would suggest that you guys all attempt the merit because it's not that much extra. And in fact, if you were doing this to try to figure out which one is which, you've already done half of the merit anyway, which is balancing the equations. So this bit here, I wrote down here again. So these are my two half equations. The other thing I need for merit is that you're linking your observations to the specific chemicals involved. All right? So just telling me why is it green, why is it brown, that sort of stuff. Cool? So that was all yesterday's lesson. And then the last thing we talked about yesterday, Angela, did you miss this bit? All right. I can give you this piece of paper once I'm done. All right. The other thing I talked about yesterday was the full redox equation because you might as well put it together. And this is stuff that we did in lesson number 1 when we were refreshing all that redox basics. We good? All right. The next two things I need to talk about then are these other excellence requirements, which is the E cell calculation and then the justification for that. So let me run you through those ideas. And I'll just leave this here. Okay, so E cell, what is that? So first thing we gotta do is think about what E cell is and what that calculation is referring to. So let me grab my marker. Okay, so the E cell as a calculation is the potential difference. Is it gone again? No, it's gone. Is the potential difference between the two half cells. So when I talk about the two half cells, I'm talking about reduction and oxidation. I'll say electrical. So when we're talking about our two half cells, we are talking about reduction and we are talking about oxidation. So now I'm writing this as separate notes instead of on the exemplar sheet because I'm just giving you some background information. So when we calculate E cell, we are taking these numbers here on your resource sheet, the standard reduction potential. So when we calculate E cell, we're taking the standard reduction potential of the reduction half and subtracting away the standard reduction potential of the oxidation half. So I'm looking at those two numbers and I'm doing that subtraction. Just going to make sure I have that the right way around, otherwise our numbers aren't going to make sense. Yeah, I was right. Reduction versus, minus oxidation. Are we okay with that so far? All right. So let me give you some information on what that number is referring to. So you guys have this whole list here that is the standard reduction potential. What you'll notice is you have a redox pair, a couple. You have fluorine and then going to fluoride. We have things like silver ion going to silver. We have the lead 2 ion going to lead. What you'll notice is that everything going in this direction is reduction, which is why it's called the standard reduction potential. Standard reduction potential. Are we okay with that so far? What's that face? That's the face of the not sure. Oh, so if I was going in this direction, so you see how you have the copper 2 ion? And then if it goes from copper 2 to copper, that is reduction. If you go from the hydrogen ion to the hydrogen molecule, that's reduction. So all of these pairs are written in the combination of showing reduction. Okay? Which, if you forget, it's called the standard reduction potential. So you know they're doing reductions. All right. Now, what you're going to notice is that there's a whole ranking of various numbers, and then there's a voltage meter written on there as well. So the higher the pair is on the list, the easier it is to reduce. So this at the top is the easiest to reduce. AKA strongest oxidant. And if you guys remember from last year, those words kind of flopped around. Because when we're talking about an oxidant, we're talking about what it's doing to the other half of the reaction. Then the bottom of the list is going to be hardest to reduce. So if it's hard to reduce, it is easy to oxidize. AKA This is your strongest reductant. Are we okay with that so far? All right. So I'm just trying to think. I will give you guys some background information on how we figure out this number. Now, this is going to be a little bit more complicated. The thing I want to add is that you never need to explain how this works. This is just background information so you understand where these numbers are coming from. Okay? Let's go and add that onto my notes. So if you don't want to write it down, you don't need to write this down. Don't need to write this down. Not assessed. Not assess. Yeah, don't need to write this down. Not assess, just extra information for understanding. Okay? So I'm just putting that disclaimer there so you don't freak out if you don't get it, because it's not actually going to be part of the assessment. All right. When we are looking at these, you see how this is just a redox couple. It's only half of the redox reaction, correct? Because I only am showing, like, for example, the fluorine. Now, fluorine obviously needs to be paired with something else, so that way there's a transition, or there's an exchange of those electrons. So the way we have to figure this out is we need to set something as the reference point for 0. For us, the reference point for 0 is hydrogen. So let me show you what the setup looks like. So how they figure out these numbers is they make a galvanic cell. What I'm drawing right now is a galvanic cell. We will learn this as the second cell you guys learn about. When they set up this galvanic cell, what they do is they have their what am I doing? That should be connected here. Okay, it's a very poor drawing, but you get the idea. Okay, oh, why did I curve that? That's annoying. Okay. Actually, no, I did want to curve it because it's going to be adding hydrogen gas. All right, so in one of our two beakers, when we have the galvanic cell, we have one half that's going to be the hydrogen half. So in here, we'll have an acid that provides the hydrogen ions. And then from this tube here, we're going to be providing hydrogen, the gas. So that way we have the hydrogen pair. All right? This here is what we're going to set as 0. And then the other side is what we measure. All right? So, what was I going to add about that? So, with hydrogen, it can be oxidized, it can also be reduced. So it can do both. In fact, all of these reactions can do both. It can go in reverse if we give it enough energy to force it to go in reverse. So, but for simplicity's sake, what we've decided as scientists is that this is going to be our reference point for 0, which is why on our sheet you see that pairing as 0. And then everything is in relation to hydrogen. So the stuff above it, these things will be reduced, and then hydrogen is going to be the oxidation reaction. Everything below it is going to get oxidized. And then hydrogen will be the reduction reaction. So that's how we kind of figure that out. This then is whatever we're testing and measuring. So say, for example, if I wanted to do copper, I'd make this the copper metal and this the copper 2 ion. I would set up this cell. This cell is spontaneous. It will do a chemical reaction without any energy input. In fact, it won't be making energy. When it makes that energy, we can read that on the voltmeter. And when we read that number on the voltmeter, that gets entered into our list over here. So if we set up this galvanic cell with the hydrogen and the copper, and I say, okay, hydrogen 0, So then copper is going to read 0.34 volts. So that's what's going to be read on the voltmeter, and that's going to be recorded for copper. Okay? Now, this is very specific because it's under standard conditions. So 1 atmosphere pressure, 25 degrees Celsius. I believe this is 1 mole per liter. Because if we change those things, it changes the numbers. So this is just standard conditions. That's why it's called standard reduction potential. So that's how we're getting these numbers. Are we okay with that as concepts? All right. So that's why that's 0. I'm just trying to see what else I had written down. Okay. So let's actually use that then calculation-wise. So that's the end of don't worry if you don't understand it. And to be fair, we will actually cover it in better detail when we do galvanic cells. But that's the idea of what we're seeing. All right. So now that we have an idea of what E cell is referring to, what these standard reduction potentials are referring to, we can do some calculations. So here's my E cell. Let me grab my green marker. All right. So for my E cell calculation, just as a reminder, you are doing the standard reduction potential for the reduction reaction. So my E cell is going to be equal to, let's see what I assigned as reduction. That was the copper 2 ion going to copper. So I find that redox pair. Copper 2 ion going to copper. That was 0.34. And then I'm going to subtract away the oxidation reaction, which is, again, what I see here with my instruction. So if I go back to my other page, I see that the oxidation reaction was chloride to chlorine. So I'm looking for the chlorine pair, which is 1.36 you're saying? Here it is. So here's my chlorine pair. So I'm using that 1.36. So minus 1.36. And then I get a value. So let me get my handy dandy calculator. You are allowed to use a calculator on this assessment. So I did that. It is negative 1.02, and we're going to put the volt on there. All right, keep going. Okay, now I need to justify what's going on. So this is the electrolysis of molten, I should actually say soluble, but we're doing copper chloride. Now, does this require energy or create energy? Requires energy. And now we're going to explain why. So what you'll notice is that this E cell calculation is negative. This number will always be negative if it is a non-spontaneous reaction. So I'm going to write that down as an extra note. So electrolytic cells will always have a negative number. If you do your calculation and you have a positive number, it means one of two things have happened. Or actually, no, 3 potential things that could happen. First potential thing that could have happened is you have these guys the wrong way around. Second error that you could have made is you grabbed the wrong numbers from the sheet. Third potential error you could have made is a calculator error. All right? Just be mindful, if you minus a negative number, what does that mean? It's positive. So just keep that in mind so you don't make that math error. Do you want me to write that down? If you subtract a negative number, you're basically adding. FYI. Cool? All right. So this is a negative number that proves that I do have a non-spontaneous reaction. What that means is that in order for this reaction to occur, I need to put in at least 1.02 volts of energy. If I didn't put in 1.02 volts of energy, this reaction would not happen. So that is what that number is referring to. So if I put in 0.5 volts, the reaction would not occur. So let's write down our justifications. So the E cell calculation shows, sorry, I should say, is a negative number. Meaning that the electrolysis, and just as a reminder, when we talk about electrolysis, oh my goodness, cannot spell electrolysis. So electricity, lysis, to break apart. So it ties in with the words you've been learning the other way. So you heard lysis and like cell lysis, cells break up. So meaning that the electrolysis of copper chloride is non-spontaneous. This means it will need at least 1.02 volts of energy to move electrons against their natural flow. So when we think about this logically, and we're thinking about our ions, chlorine, for example, has 7 electrons in its valence shell. Gaining 1 means that it'll be stable. So it will be stable if it becomes the chloride ion. I am trying to force it to do the opposite. Since I'm forcing it to do the opposite, it's going to require energy. So I'm forcing the electrons to move in the opposite direction than they naturally would want to occur. Make sense? Hopefully. Okay. All right. So I'm moving the electrons against the natural flow. What this is also going to do, it's going to consume electrical energy, which is what we did. We plugged it in. And it's going to create a chemical reaction. And in that chemical reaction, we're now going to store that energy as chemical potential energy. So now my energy is being stored in the bonds, which is pretty cool. Actually, I should rewrite that. That's not a good sentence. It consumes electrical energy. Sorry. To create a chemical reaction. So in this case, the chemical reaction is Cu2 plus the 2 chlorides becoming Cu plus Cu, or Cl2. That stores chemical potential energy. So when we're thinking about the electrolytic reaction, we're going from electrical energy to chemical energy. When we do galvanic, it's going to work in reverse. And with galvanic, a lot of galvanic stuff is going to be stuff like batteries. So batteries are an example of stored chemical energy. And when we complete the circuit, you can then get electrical energy from those batteries. We good so far? All right. The other thing to keep in mind are the E cell values. So what we can see is the chlorine chloride pair is positive 1.63, and the copper 2 ion and the copper pair is 0.34. So if I was to look at this list, the chlorine chloride pair is the stronger oxidant. So I'm going against the natural flow. So in order to make sure that the chloride doesn't become the natural oxidant, I need to do energy being input. So the standard reduction potential of the Cu2 plus Cu is less than the Cl2 Cl. All right. So it makes that the weaker oxidant. Do you agree with me on that? All right, so because it's the weaker oxidant, I need energy to make the reaction occur then. So further supporting the need for energy to make it the oxidant. I know that's a lot of writing, but that's what the excellence is looking for, is that understanding of what's happening. All right, any questions about that? I'm just mindful of the time because I want to make sure you guys don't listen to me all session. Cool. So it's a reasonable jump, I would say, from merit to excellence in this case. Which last year wasn't really like that. All right. While you are writing that, I'll tell you guys 2 stories so we can think about application of electrolysis. This, again, isn't going to be assessed. This is more so just fun information for you guys to know. So the whole idea behind electrolysis is that we are trying to purify substances. So we're trying to get to our elemental form. So fun fact, aluminium was once the most valuable metal to humans, which is crazy because we buy them at the supermarket and we like rip it, roast our dinner on it, crinkle it up, throw it away. But back in the day, in the 1800s, aluminium used to be, like I said, the most expensive, the most precious metal. So they would make jewelry out of aluminium. You'd have like aluminium lockets and like necklace pendants and earrings. You would even have aluminium cutlery. So like if you were the wealthy of wealthy, you wouldn't have gold cutlery, you would have aluminium. You know how we call cutlery silverware because it was made of silver. So aluminium used to be the most expensive metal, which is crazy. Overnight, the cost of aluminium dropped, and that was thanks to chemistry. So aluminium is actually the 3rd most abundant element on this planet. However, even though it's so abundant, we don't actually have easy access to it in its pure form because it normally oxidizes with air to form aluminium oxide. You okay with that? So aluminium oxide, we know ions are very different from metals. We know that from structure bonding. So what they do is they do the electrolysis process and they are able to purify aluminium that way. And that's how the price dropped overnight. So some scientists figured out how to do that, And once they did that, there was supply and demand, and then aluminum is now just an everyday metal that we use. So I thought that was a crazy thing to learn. This does require lots and lots of water because it's a very hot process because you have to melt things down. So it's useful if you can recycle your aluminum to kind of save money and things like that for the developers. I mean, like I'm drinking out of a can right now, and that's aluminum. So that's how readily available it is. That's why we don't use glass and stuff like that anymore, because we could figure out how to manufacture that. So that's kind of a fun fact for you guys. The other fun fact that I have to tell you guys about electrolysis is that not only can it be used to purify stuff, but it can be used to plate things. So you guys know how there's like various qualities of jewelry? Have you guys ever bought a ring and then your fingers turn green from that ring? Or like you put on earrings and your ears turn green? Or your necklace, your neck turns green? You get really aggravated, right? That is because a cheaper metal is hiding underneath the expensive metal. So like how you guys were doing this electrolysis reaction here, and the copper coated the outside of the electrode, we can swap out the carbon electrode for a metal electrode. Say, for example, a cheap metal like copper or nickel. We put that in the electrolysis, and then in the solution, we have a solution of gold, or we have a solution of the silver ions. We do the electrolysis, we turn the electrolysis on, it coats the outside in a very thin layer of silver or a very thin layer of gold, and then you sell it as gold plated or silver plated. But obviously it's just plating, it's not actually the gold or the silver as a full thing, so eventually that wears off. So that's why when you have that cheap jewelry, you'll see that it looks like it's like scuffing up and stuff like that, and you can see like a metal underneath it. That's because you're losing the plating on the outside, which I think is funny. So that's why when you go shopping for jewelry, if you see it's like gold and it's really, really cheap, it's probably fake. There's probably gold layering on the outside, but not the inner gold. So if anyone gives you cheap jewelry, you put it on and it turns green, you now know why. Because the copper reacts with your skin and it turns it green. All right, questions, concerns, comments? Anyway, that's 2 ways that electrolysis can intertwine into our lives. Alrighty, cool. You guys have the rest of the session to study. I also have a little surprise for you guys.